So in the very first scenario, I would be discussing the definition of a compact set. So what do I mean by a compact set? So, well, how would I say the set is compact? I would say that every open cover has a finite subcover. So let us decode this statement now. This is the official statement. Now what does it mean? So suppose that, okay, let's try to do it this way. Suppose you have like a space or like a set. You have a set and let's call it X. Now what I mean is that given any open cover, so by open cover I mean collection of open sets such that, let's consider it. So like there are infinite amounts of these. I'm only drawing a few of them, but they're like, assume they're like an infinite number of these sets AI. So I have that X is a subset of the union of AIs, and I have a family of sets. So given any open cover, that is any family AI. So let me write it as I belong to the family of open sets. So there's a family of open sets with X is a subset of the union of all AIs. So now what I'm saying is a set is compact is that I can always find a finite subcover, meaning that earlier it was an infinite number of such open sets which used to cover X. By cover X I mean this condition. So this is what I mean covering X. Covering X is this. So now what I'm saying is, rather than being an infinite amount or number of such AIs, if I can always find a finite subcover, meaning that I have AIJs, j equals to 1 to n, with this property, then I said that my X is compact. Then X is compact. Okay, so that's the basic definition. Now let's carry on. So the next thing that I want to talk about compact set is, well, every sequence as a convergent subsequence. So this is another definition of a set being compact. If I take a sequence in that set, then there has to be a convergent subsequence, and then this is applied for every sequence. The next thing that I would like to talk about is that Banach spaces and normed vector spaces are never compact. And one more definition or one more fact related to set being compact is that if X be a subset of Banach space, then if X is compact, then X is closed and bounded, but not the other way around in general setting. But if we are in the case of a finite dimensional setting, then closed and bounded also implies compact. And one final formulation of compact is that if X is compact, if and only if X is closed and totally bounded. Now, what do I mean by totally bounded? I mean that for every epsilon greater than 0, there exist points such that X is contained in the union of all such balls. So if this is the case, then I also say that X is compact. Well, if you look at this definition, then it corresponds somewhat to the definition of every open cover has a finite subcover. So this is somewhat reminds me of that definition, if you try to connect those two ideas together. Now I need to tell you the definition of something being relatively compact and that of a compact operator. So a subset M of a norm space X is called relatively compact if closure of M is compact. And the second thing is that X and Y be norm spaces. A mapping T from X to Y is compact if T maps each bounded subset of X to a relatively compact subset of Y. Now the next thing that I'm going to talk about is some properties of relatively compact sets. So I said that M is relatively compact. It means that M bar or M closure is compact. Now characterizations of relatively compact. So I say that M is relatively compact if and only if M is totally bounded. And what was this concept of totally bounded? So totally bounded was for every epsilon greater than 0. So let me write it here. So for every epsilon greater than 0, there exist points x1 to xn such that your set X, whatever subset that is in consideration, is contained in the unions of balls around these points. So if this is the case, then I say that it is totally bounded. Now M is relatively compact means that M bar is compact. Now M bar is compact if M bar is closed, then M bar is totally bounded. Now I already know that anything with a closure is definitely closed. So this condition I can skip out. So I can say that M is relatively compact if M star is totally bounded. And that's exactly, well, not M star. So M is relatively compact means closure of M is compact, which means that closure of M is already closed and closure of M has to be totally bounded. So now a very subtle note here is that M star is compact. M star is compact means that M star is closed and M star is totally bounded. But M is totally bounded or M star is totally bounded are, well, one implies the other, because if I can cover the closure of M with balls as here, then I can cover M also with that. So one implies the other, so you do not need to be too much fussy about this issue. And the second thing that I would like to talk about is M is relatively compact if and only if every sequence in M has a convergent subsequence. But now you have to take a note that the limit might not lie in M. I'm so sorry I drew this M so dirtily, to be honest. Let me draw the M again. Okay, so limit can lie in M closure. So that's the case, because yeah, in the earlier case we did that the limit must lies in X. So when I define the concept of a compact set, I said that every sequence has a convergent subsequence. But what I mean by convergent subsequence is that the limit must lie in X. That's the point. That's the point here. But in that case, the fucking limit can be in M closure. Okay, so that's the only difference. So yeah, so that's pretty much what I say, that let X and Y be norm spaces. Then I say the mapping T from X to Y is compact if and only if each bounded sequence xn in X, the sequence txn in Y, has a convergent subsequence. So how do I proceed with it? I proceed with it as follows. So I say, so now definitions would help us to deal with this. So I say X and Y are norm spaces, a mapping T is compact if T maps each bounded sequence of X to a relatively compact subset of Y. And what do I mean by relatively compact subset of Y? So which means that Y closure is compact, which means I take any sequence or every sequence in Y closure, it has a convergent subsequence. That's my point. So what I need to prove here. Or if I take any sequence in Y, it has a convergent sequence, but the limit might not lie in Y, it might lie in Y closure. Okay, so now what do I have? I have like, so we have to prove two ways. We have to prove that if T is compact, then for each bounded sequence xn in X, the sequence txn in Y has a convergent subsequence. So how would we prove that? We take that, we start by assuming that let T be compact, and we say that let xn be a bounded sequence in X. So what do I mean by bounded sequence in X? I just means that if you take the moduli of anything, it is less than some quantity, say M. Okay, so now that this xn is in a ball of radius r around 0, which I can always take this assumption, because yeah, I can take any points here and I say that okay, I can take any points here and I say that okay, my mod xn is less than some r, not the real r but say some r, and I can say that all these xn lie in a ball of radius r. Now I say that since TBR0 is relatively compact, so what does this mean? It does mean that TBR0. So why do I say that TBR0 equals relatively compact? I can say that, well, this is compact, and my definition of comp as a set, let me first put it, so this is compact as a set. Now T compact as an operator, T is compact as an operator, it means that this thing here without the closure, so let me write it down again, so TBR0, this should have a convergent subsequence. If that is the case, so since TBR0 is relatively compact, because this is what my definition of compactness lies, so if T as an operator is compact, it maps each bounded subset of X, well, the ball of radius r around 0 is pretty bounded in my opinion, so it is a bounded subset of X to a relatively compact subset of Y. So what it maps, so it's saying that TBR0 is this thing which is relatively compact, because this is what T maps the ball of radius r around 0 to. Okay, T maps the ball of radius r around 0 to this, which means that this is relatively compact, which implies that the sequence txn has a convergent subsequence. So how do I know this is a sequence? Because, well, T is compact means T is bounded, means T is continuous. So continuous operator map bounded sequences to bounded sequences. So this sequence here is also bounded, and I say that, okay, now TBR0 is relatively compact, which means I take any sequence in my set and it has a convergent subsequence. So I proved the point that, okay, if T is compact as an operator, then the sequence Txn and Y has a convergent subsequence. That's exactly what I proved now. Now the next thing that I need to do is, now suppose that for every bounded sequence xn in X, the sequence Txn in Y has a convergent sequence. So this is my assumption now. This is, what given to me, and now I need to prove that T is compact as an operator. So let's start with this. So let M be a bounded subset of X, okay, and I say that, let me see which space I am operating in. Okay, so the X is the norm space, so it's okay. So M is a bounded subset of X, okay. So Txn be a sequence in Tm. So we have these two things given, okay, this separate and this separate. So Txn is a sequence in Tm and M be a bounded subset of X. Now this is, now we have to do is, you have to see that each bounded sequence xn in X, the sequence Txn in Y, has a convergent sequence. So this hypothesis is given to me. I have already know that each bounded sequence xn in X, the sequence Txn in M, has a convergent subsequence. So I start by saying that Lem be a bounded subset of X and Txn be a sequence in Tm, okay. Now since M is bounded, okay, I can say that Xn is bounded, of course. Well, this is a very trivial fact, and I say that since Xn is bounded and I have Txn has a convergent subsequence. So see, I have this condition given now. I know that Txn is bounded and I know that Txn has a convergent subsequence. So what was the definition of T is compact as an operator? Well, if T is compact as an operator, if it maps each bounded subset of X to a relatively compact subset of Y. But I know that Txn is Y has a convergent subsequence. So I know that if I prove that Tm is relatively compact, then I would prove that my operator T is compact because it maps a bounded set to a relatively compact set. And what would I need to prove that Tm is relatively compact? I would need to prove that if I take any sequence in Tm, it has a convergent subsequence. But it just happened. If you just look above, when we went the other way around, we said, okay, let's take Txn be any sequence. Now I know that if Xn belongs to M, then Xn is a bounded set, then Txn also has to be bounded because T is linear and bounded. Well, I'm assuming T is compact, so obviously T has to be bounded. So Txn is a bounded sequence in Tm. Now, step 3. Now in step 3, what I have is, it's given that if Xn is bounded, we know that Txn has a convergent subsequence, has a convergent, let me write it down here, has a convergent subsequence. Now this is given as a part of my construction. So if this is the case, then I can see that Txn was any sequence in Tm, and now any sequence in Tm has a convergent subsequence. So it means that Tm must be relatively compact. So that's proven, and T is compact in sense now. So what I essentially proved here is, I say that let X and Y be norm spaces and Tx to Y be linear and compact, follows that T is bounded. Now T is bounded as an operator. I have to prove that. How would I prove that? If I prove that the soup of this Tx is less than infinity, I can prove that T is bounded and hence continuous. Now I know that as a set, okay, let's look at this way. So this is a bounded set and T is compact. So the closure of T B10 is compact because that was the definition, that T is a compact operator if it maps bounded sets to relatively bounded. So T dou B10 is relatively compact, so the closure of T O B10 is compact, and hence it is bounded. Now it follows that the soup of this thing, like T maps it from X to Y, would be less than equal to. So technically it should be equal to, the actual definition works like this, that it is equal to soup of Y, and where Y is in this range. That's what my scene was. But now this is definitely less than y being in the closure of tb1 t dou b10, because of course, and again soup of y, and I know that this thing is compact, which means it's bounded, so that soup of y in this range would be less than infinity. So the last thing that I would do now is that I have a proposition that says that let x and y be norm spaces. A mapping from t x to y with dimension of t less than infinity is compact. So I have to prove the compactness of a set now. So I know that, well, if I show that closure of tb1 is bounded, no, this is what I need to show, that is well, I need to show that the closure of tb10 in image of t, so not in y, but the closure lies in image of t, is a compact subset. So I have to show that tb is a compact subset of mt. How would I show that? Well, let's start. I know that t10 is bounded, fact number 1. Now I know that t is a continuous function from x to y, so tb10 is bounded, which implies now I will do step 2 and step 3 in one. So if tb10 is bounded, then the closure of tb10 is bounded and closed, because I just closed it. Now if the closure of tb10 is bounded and closed, and since I am in a finite dimensional setting, if you see image of t, dimension of image t is less than infinity, so in finite dimensional setting, closed and bounded means compact, and thus we have the proposition. Now if you see carefully, the closure that we have taken here is in the image of t rather than in space y, because I know that the dimension of image of t is less than infinity, so it's finite dimensional. So if I have closed and bounded as a close in a finite dimensional setting, then it implies compact. But if I have something like that in finite dimensional, y might be infinite dimensional, so I cannot take y, or I cannot take the closure in y. I have to take it in dimension of image of t.